So what we are going to attempt to do now is we are going to attempt to draw on a flat sheet of paper a two-dimensional representation, it's flat, we're not building a model, of what this might look like in 3 dimensions. What does it look like? What is its shape? Which way, you know, I keep saying that this shape that we're seeing isn't real. This is not. If you look at this, you say, well, this thing is just a straight line with something shooting off of there, right? That's what it looks like. That's not what it looks like. We're going to see how we can determine what it actually looks like in 3 dimensions. And here's the key. What we're going to do is we are going to look at hybridization, and we're going to rigidly follow what the hybridization says is going to happen, and just kind of go from there, follow where that leads. And so I'm going to attempt to, in this big space, you're never quite sure where it's going to end up, so you got to kind of leave yourself a lot of space to draw this. So what we're going to do is we're going to draw this. We're going to draw these hybridizations according to a few rules that I'm going to teach you as we go. So the first carbon on the end here is an sp2 hybridized carbon, right? So we're going to start over here somewhere. I'm going to draw an sp2 shape, which is what shape? Trigonal planar. So I'm going to draw a trigonal planar molecule. Doesn't matter how. Any old way you draw. Oop, that's not right. I have the worst trouble drawing 120 degrees freehand. Doesn't seem like it should be that hard. So, again, we're not all artists. Your drawing may not look any better than mine, and that's okay. But what did the sp2 all have in it that I haven't drawn yet? It has an unhybridized p orbital, doesn't it? And we need to go ahead and include that for now. And I'm going to use a different color for my p orbitals. You might either use a different color if you have it, or just use dotted lines like I did in the previous. So I'm going to draw this unhybridized p, and it gets really hard drawing it in a 3 dimensions is kind of hard. So when I look at this, I've drawn the sp3 in the plane of the board so that the leftover p should be going perpendicular to the plane of the board. That's kind of hard to draw, so we have this unhybridized p coming in and out of the board like that. Okay? Now, this next carbon attached to it is going to be the same shape, right? Now don't draw it yet. Watch me draw it first. We're learning how to do this. For this next molecule, or next atom I mean, this next hybrid orbital, what we're going to do is we're going to draw an sp2, but here are the rules. The sp2 has to have, see how it has 3 lobes? One of the lobes has to overlap with one of the previous lobes directly, like pointing face to face, like this. Not like in at an angle. They have to overlap exactly. So the first lobe I'm going to draw is a lobe that overlaps this one. That's actually what this bond is. This bond constitutes this overlap of two of these sp2 orbital lobes. So here we go. I'm going to start with this. Okay, see what I did there? Just straight across. And now on the end of that, I have to draw the rest of whatever an sp2 would look like, which I'm not very good at, but something like that, right? See what I did there? I did a poor job of it, but let me show you what people do that's wrong, just kind of get you an idea so that you don't start doing it wrong. Some people, I won't draw the unhybridized here. They'll start with that guy, and then they'll be, oh, there's an overlap here. You see how that's not right? See how it's not coming directly off of it? It's not overlapping. They got to be pointing straight at face to face there. That's very important. That's how we're going to get our shapes. Okay? So this is wrong. Don't do that. straight across. They need to be making a straight line. Okay? Now I left off my other unhybridized P, didn't I? So I'm going to put that in there. Now, do you want to go to the right or do you want to go up next?
Up.
Up. You want to go up? All right. So we're going to go up. And the thing we're going up to is the carbon with what hybridization? sp3. So where is that coming off of here? Is it coming off of this lobe? Understand that every time you attach a new atom, what you're doing is you're overlapping a new hybrid with a new hybrid lobe with an old hybrid lobe. That makes sense? I speak in German. So we're going to want to, this guy, one of its lobes has to overlap with what here?
Top one.
This top one, that's right. Now it turns out that we could just as easily do the bottom one and get the same shape. But you'll just have to trust me on that. So in other words, it doesn't really matter where you do this. But kind of looks like top there, so we'll go top here. So I'm going to draw my overlap first, and that's not intentionally long and skinny, it's just that I'm bad at drawing. And then what's the rest of this look like? Well, this is an sp3 orbital, right? So this is one edge of a tetrahedron. It's almost like an upside down tetrahedron, you know, rather than having the top going this way, the top's going that. So I'm going to have these three lobes, something like that. Again, I'm bad at drawing, you're bad at drawing, that's okay. We just want to make sure to get it straight as we can. Okay?
Why is it upside down?
Why is it upside down?
Yeah.
It's, well, how do you want to draw it? But what it is remember that this, here's what we have. We have this is the shape we have. We have this shape, right? This is the tetrahedron, this is what we have. And we know that one of the lobes, any lobe, it doesn't matter which, is overlapping here, right?
Yeah.
So when you do that, the others have to point that way. Got it?
Yeah.
So, does that answer your question?
Yes.
Good. So, this then is that atom. And by the way, we're not drawing the actual C's, the carbons, but notice where they are. They'd be right on the vertices and the centers here. This would be a carbon, this would be a carbon, this would be the carbon. All these lobes represent the electrons. All right, so we've done this one, we've done this one, we've done this one. So now we got to do this guy. And where is it and what should it look like? Where is it coming off of? It's coming off of this lobe, right? Yeah. This is a really important skill. You got to be able to tell where it's coming off of. This is where it has to come off of one of these lobes, and this is the only one available, right? And what shape is it? Shape we got to do. Well, let's do the overlap first. You see how this is telling us what shape it has to be? Because it has to line up directly with that lobe, we know which way it's got to branch. Okay? And it's an SP, so you just got the straight line thing there. And now, we've got to draw what else? For an SP, what's left over? Yeah, we got two different. And so these get kind of messy. I'm not going to worry too much about orientation in space, but I got two leftover P's there. Okay? Next.
Get another one, right?
Get another SP. So that's going to line up straight aways with it, isn't it? Another. Line up. Line up. And again, more unhybridized P's. Almost like butterflies. Okay? So that's done. Oh, we're getting close to the end. Next guy is SP3. So again, you always start with the direct orbital overlap, and then you see, well, where does the rest of it have to go from there? Well, this is a tetrahedron. So this is a tetrahedron with its top pointing that way. So we're drawing this. We're trying to draw this. So what does that look like? Well, it's kind of hard to draw, but something like that, right? And any unhybridized P's there? Mm-mm. And finally, yes, finally, we're to the last carbon. And the last carbon is sp3. Where do we put it? We kind of have a choice here, don't we? There's really no wrong answer, so put it wherever you like. But just to realize, this is kind of going down and into the board a little bit. This is going up and into the board a little bit. This is going out and out of the board a little bit. It's three-dimensional. So whatever. There we go. Does it say how long this video is?
11 minutes.
Ooh, I better hurry. Actually, I don't think I have to keep it under 15 because I'm special. Special dispensation from YouTube. All right, so we've done all the hard part, but we still have a couple things we need to do. One, this kind of bond here, where we have an orbital overlap, we have a regular hybrid orbital overlap, that's a certain kind of bond. That's called a sigma bond. All of these overlaps are sigma bonds. Have you used sigma in lowercase sigma in your math classes ever? You probably used the capital sigma, right? No. Lowercase sigma. This is a sigma bond. 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 Every time they overlap, it's called a sigma bond. What have we not drawn here yet? What's that?
Hydrogen.
That's hydrogen. Did we draw that here? We didn't. Turns out the hydrogens don't affect the shape at all. We just kind of stick them on, right? So there'd be a hydrogen here, and hydrogen's just an s orbital, so there'd be a sigma bond with the hydrogen there. Basically, every time you have a lobe that's not pointing anywhere, that's got to be a hydrogen. This is how we would tell where the hydrogens go. So there'd be a hydrogen there, sigma bond to a hydrogen, sigma bond to a hydrogen, not the P's. Any hydrogens to put here or here? Any lobes not already overlapped? Every lobe has to be overlapped, so one here, one here, one here, one here, one here. That's sort of a way to check that we've done it right. We should match up the right number of hydrogens with our original formula. And finally, what of these unhybridized p orbitals? Well, they do something kind of special. Turns out that orbital overlap is a good thing energetically. It lowers the energy of the molecule. Anytime you have orbitals that can overlap, start sharing, that's a good thing. So here we have an orbital, and here we have an orbital. The molecule would like these to sort of overlap, but they're kind of not pointing towards each other, are they? But they're parallel. You notice how these are parallel? And actually, every time we look, we can actually find a set of parallel p orbitals. So this one's kind of going in and out of the board. This one's going in and out of the board. And what's going to happen, anytime you have two adjacent parallel unhybridized p orbitals, something magical happens. They actually sort of reach out, stretch out to each other, and form a big sort of ring-like structure of electron cloud known as a pi bond. That is called a pi bond. So we have our sigma bonds, just the regular old normal overlap of orbitals, of hybrid orbitals, or a hydrogen would be a sigma bond. But when you have these unhybridized p's that create this ring electron structure. That's called a pi bond. Now let's look at these two carbons here, this one and this one. Oh, wait a second, you guys are drawing your pi bond. So let's focus on these two carbons here and here. One thing you'll notice about them, what kind of bond do they have between each other?
Sigma.
They have a sigma and they have a pi. They have a sigma and a pi. That is a double bond. Sigma pi, double bond. Whenever something has a double bond, there are actually two separate geometrical features, the sigma bond and the pi bond. So we should be able to identify 3 bonds when we get to this guy, shouldn't we? So let's move on down the road. So let's look at these. So we've got this guy all taken care of. Now let's look at these two. Notice, do you notice a kind of an up and down p orbital here and an up and down p orbital here? Pi bond. But what else have you got? An in and out one and an in and out one. So we've got another separate pi bond going in and out of the board. Sigma, pi, pi, triple bond. And now everything's accounted for. We've got our triple bond accounted for there, single sigma pi pi. We've got our sigma here, sigma, sigma, sigma. It's all taken care of. And take a step back now and look at this molecule we've just drawn. Does it look like that at all? Does it look anything like that? This is not what this looks like. It looks nothing like that. It looks like this. It looks like this. This is what that molecule looks like. If I hold it up here. Now, I don't know how well you can see this on the video, but here's my double bond down here pointing out that way with my hydrogens going up and down over here. Up to my tetrahedron, upside down tetrahedron there. Single bond, triple bond, straight, triple bond here. And then I get out to here and wait a minute, this one has it going up, that one has it going down. I said it didn't matter, it doesn't. It's the same thing, whatever. These actually can rotate. These single bonds on the end are able to rotate. So it might depend on what temperature it's at when you take the picture. So, but this is a very different picture than what you thought you saw whenever you built that molecule in the first place. And we should stop the video.